Hey everyone, it's Sam, the Reclaimer developer here again, and today I actually wanted to go over the code base and the state of the Reclaimer. So, I've mentioned I in my last video I actually went over how I like to develop C++ on Windows, and I've in my very first video I talked about how this has been a project that I've been working on for a couple of months, so I'm not necessarily starting from a clean slate. I'm definitely not starting from a clean slate tonight. So I just wanted to take a few minutes. This is probably going to be a short video. I say that, and it could be another 20-30 minute video. But I just wanted to go over what the code base looks like and just kind of go from there. So I'm in this is just the current branch that I'm working in, but this should be familiar if you saw my introduction to how I like to program, but I'm just going to go ahead and collapse everything and just sort of go over the structure of the project. So, in the root directory, you'll see that I have these are just my workspace settings and the settings for the C++ project and my build tasks. So currently everything is in here in this tasks.json file. I would like to extract these into their own bat files because it is my goal to make this code base as flexible as possible so that anyone with an editor could potentially work on this. Right now, you have to have an instance of VS Code or something that can reason about these JSON files in order to build it. So I don't care if someone wants to use Visual Studio or VS Code like me or Emacs, Vim, Sublime, I don't care. Just I want to give people that option if I ever have anyone working on the code base with me. So if I hit Control B, I have these build tasks, and the build all, it does exactly that. It just builds everything. So I believe when I was working on this a bit last night, so yeah, it takes about 5 seconds to build the entire code base, and I'm going to go ahead and run it because I'm sure that's what everyone wants. You'll see that there's not very these images are the Skybot from the Skybox tutorial on learnopengl.com. I'm by no means an OpenGL expert, but this is just basically the canvas, sort of like the blank slate that I'm starting with. So I've just got something that I can reason about in 3 space, and there's this little cube character who is just meant to be a placeholder for the main character as I work out the user controls and stuff. And so you can see that I can just move him around. If I hold the shift button, he speeds up a little bit. It's nothing really to, this is basically nothing. If you were to take any intro to computer graphics programming class in college or something like that, you would be doing something very similar. So this is basically nothing. But something I want to point out is I'm just going to go ahead and pull up an example like from the Unreal default scene. Like the Unreal Engine default scene. And just kind of do a little bit of a comparison. I'm not trying to make this an Unreal Engine clone. I'll kind of get to the fundamentals of what I'm doing. But if you notice, like this is the default scene that appears in Unreal Engine. And you'll notice that it's basically nothing too. It looks a lot prettier than what I have. But in the same vein, it's also just a blank canvas. So this right here is meant to just be like, okay, you've got these simple objects. in just a simple space with a grid map that shows you the orientation of, the objects that you're working with, and you can just move things around, which is basically the same thing that I have right here. Only mine is like 90% from the ground up. Like, I started with basically nothing. Um, but that isn't to say that I'm such a great programmer. In fact, I consider myself, very much not an expert programmer. It's just showing that there's not a whole lot of mystery behind what I'm doing. It's not that it's simple. Like, these concepts are not easy. I'm definitely struggling to understand them myself, and it took a long time to get to this point. Um, Tutorials and everything are great, especially when learning OpenGL because there's such a steep learning curve. But um, there's not a ton going into this. And it just took a couple of months. And while I don't have a lot of the fancy tools and functionality that Unreal boasts, it didn't take a ton to get to this point. That it's like, I can compare a little bit, where it's like, okay, there's something going on here. And so I'm not going to be doing like weekly streams. I'm not really going to have a schedule as to what I'm doing right now. It's mostly just going to be updating whenever there's something noteworthy to update. This isn't what I do full time. Like, I have a full time job where something that's not working on game development. So this is going to be done in my spare time. But I want to, at this point, go over what the actual code base looks like. So let's go ahead, and that should be stopped. Let's go ahead and close this. And let's just go ahead and start taking a look in the source. So everything starts in this reclaimer Win32. And in this platform file is where we find our win main. And again, if you want to learn a little bit about how I do things with the Windows API, how I make applications and libraries and how they can interact with each other, definitely check out my previous video. I'll try to link that in the in card of this video. But here's our win main, and we just have a simple loop. Or we have a simple little setup where we essentially create a window. It's called the reclaimer. We have our window context, and I have all of these function pointers that allow the game to call back to the platform. And so I do this in the hopes that this could potentially be cross-platform. There's a little bit of Windows API specific code in the game right now, but how I want to do things ultimately is that the game itself, like the actual core of the game, is platform non-specific. So meaning, as long as you have a compiler that can compile the program and you have a way to populate these platform callbacks. So like, the implementations of these are going to look different, like if you're on Linux or if you're on Mac or if you're running off of an Xbox or a PlayStation or something on Nintendo for that matter. But as long as you have a way for the game code to call back to the platform and say, hey, there's a resource on the file system or memory I need to allocate that is specific to how the operating system does this. And as long as there's a way for the platform to pass that data back and forth, it should just work. So, but right now, it's only on Windows. And so we set all that up. We get the initial window dimensions, and this should look really similar to what we did last night, where we made a very simple API that we initialized. We have a simple state where we create and initialize the reclaimer, which is the reclaimer state is a data structure that essentially gives us access to every single bit and byte of the game's memory. So every possible thing, everything that's going on is going to be accessible from this structure. And right now, there's only three functions that the API exposes: create the state, update and render the state, and then destroy the state. So, and that happens on creation of the window, during the main window update method, and at the very end of the program when that loop breaks. So right now it's if I just hit the escape key or hit the close window button at the top right. So that's basically it at a high level. So uh, and everything else is just related to processing user input and getting stuff from the operating system. So, for instance, um, I use the Windows API uh, in place of the C runtime libraries, and the reason I do that is a lot of the methods in, from what I understand, a lot of the methods in standard IO sit on top of the Windows API. So there's just sort of a layer of abstraction there that I'm getting rid of by just calling these Windows functions directly. I could be wrong about that, but that's how I understand it. So, like, for instance, if I were to call malloc, for instance, like to allocate memory, there's going to be that's going to translate to something that Windows can understand when it already understands like virtual alloc or heap alloc or something like that. So it's going to do it's going to I'm just skipping that process. That could be incorrect. You know, someone please correct me if I'm wrong, but that's just how I'm doing this. And it's I could be using a library like the Simple Direct Media Layer or SDL2 library, but I just prefer to do things this way. And honestly, the Windows platform layer is like the platform specific code is almost complete. Like, there's not a ton of stuff that needs to go on. Just the platform needs to have a way to read files, allocate and deallocate memory, and did I say process user input? Like, just to be able to process user input and uh, manage resources, allocate, deallocate memory, read files, and that's basically all that it does. I've been working on this for several months, like I said, and I rarely update this, file IO. The platform specific code rarely gets touched unless I'm doing some mild refactoring. So, and when it comes to user input, this looks like a mess, but what I'm doing is I'm essentially just packing the I don't think it happens here, but I'm just essentially translating, excuse me, the Windows the key codes that a user can input using their keyboard from what Windows understands to a reclaimer specific key code. And that's all packed into a tight array of bytes where each bit in that array represents a key code that is pressed. It's pretty simple stuff, and like it would be really similar depending on which platform that it's on. But essentially, you would have the Windows that consumes the API for the game, and Windows just says, "What do you need from me?" And then Windows fills out what it needs and then passes it back. So with that, we go into our first library for the game, which is the Reclaimer core. And unfortunately, this is a bit of a mess. I keep saying that a lot, but we just have a simple function that initializes the Reclaimer state. And while I'm on that topic, let's take a look at the state. So, I have a bool that tells me that if it's running or not. And we have our delta time, which is the difference in time between when the last frame was drawn and when the current frame was drawn. And so this is a way that pretty much every single graphics program keeps track of time. and processes user input. So, like, if I were to just process, like you saw that the cube was moving around, for instance, if I were to move the camera around and move that cube around at full speed, it would be gone so fast you wouldn't even be able to see it. So there's a lot more that the delta time is used for, but just one simple example. It's used universally sort of as like a constant that just scales things down. So and there's the scene grid, which you saw the grid that was being rendered. I can go ahead and just run the reclaimer and have that running side by side so we can kind of see what I'm talking about. So the scene grid is this grid down here, which is just a collection of lines. That's all that it is. And then there's the state of the other libraries. So there's a library for rendering and there's a library for the models. Currently, there's only two. There's the skybox and there's this purple cube that's called the static cube. And there's also only two renderers. There's a renderer for, and I say renderer, but it's really a shader program. I'm probably going to end up renaming, like if you see the word renderer in here, it's probably going to be changed to a shader program. But there's a shader, there's actually three. So there's solid shape, which the lines are used for. There's the static, the textured renderer, which this graphic right here is like this purple cube with the small square in the center and the black outlines. That is a bitmap. And so that's actually being textured on. And then there's also a shader for the background skybox. And currently that's all there is to it. And of course, it uses OpenGL. So I essentially just have this base library that contains all of the OpenGL functions that I need to essentially bind and create buffers. In the renderers, is where I do the actual render calls. So we can just go ahead and take a look at those right now. The simple one, I think, is going to be the solid shape one. So when I create I just pretty much use structs for everything. And inside of these render programs is pretty much just storing the ID that OpenGL gives us. So when I say GL use program, this is the ID that's being used. The actual matrices and vectors that the shader program is going to be manipulating, that is going to need passed into it, and then the uniforms, which these are going to be the locations where when I say I'm going to need you to update the projection matrix with this value, this projection matrix right here is how we're going to find it. We're going to tell OpenGL, hey, this projection matrix has this ID. This is where it's located. And then you pass in this value and tell it, hey, this is the value that I actually need. And so we expose a simple API to update the matrices and update the color. And that's how that's how the rendering is being done. And if I go into the header file for the rendering library, we start to see a pattern here for how I'm sort of containing all of the different functionalities and separating everything. So we just have this simple API that can be called from the core to create certain renderers and to update them, and also to expose, hey, if I need OpenGL to do something, I can just access the OpenGL API that I have. And the last thing that I want to go over is the math library. Now, the math library is really basic, and again, I could be using the, I think it's GLM. I know it's called GLM, but I can't remember what that stands for. Was it the, GLM library? Yeah, OpenGL Mathematics. Now, I'm doing something very similar, but I'm writing the math functions that I need as I go. And The resource that I'm using for that is this book called The Foundations of Game Engine Development. And the author is Eric Lingiel. I can't pronounce that, but I'll put a description of that, a link to that on Amazon in the description. It's a fantastic book that pretty much everything that I've been doing has come from this. And it's given me all the resources that I needed to build my own mathematics library. So, for instance, this is actually the first bit of code that I worked on when I started this project. I wanted to learn how game mathematics worked, and so how to do, matrix manipulation and whatnot. And I'm not very good at math. So, like, I do have an engineering degree, but, math is not something that comes naturally for me. So, for me, it just requires a lot of practice and a lot of research. And this started out as an exercise to teach myself all of this stuff. And this is sort of what it turned into. I started out coming up with a simple math library and then started building this game around it. So, and so this is, like right here, this model view projection code is what I use to calculate all the orientations for everything in three-dimensional space. So this is primarily what the camera uses. So when I'm moving the camera about, this is essentially what it's calling. So there really isn't too much more to it than this. It's very, very simple. It's a bit daunting because, like, you'll notice there's a lack of generics, so everything is basically hard-coded. And, well, for one, I haven't had a use for them right now. Generics, so templates, would basically murder your compile times. And as you noticed, there's currently, I believe, there's 3 libraries, 1 executable that's consuming those libraries, and the entire project builds in 5 seconds. And it's going to stay very similar to that, I think, through most of the project. As we start adding a lot more custom code, that compile time could increase by, a lot. But currently it builds fast, it runs fast, and it's something that works for me. And so when it comes to mathematics, at least in terms of game development, especially with an OpenGL context, everything is done in floating point operations. So that sort of really puts a limit on the types of, mathematics operation I need to do. So for instance, these I have these functions that do operations like adding, subtracting, normalizing vectors, and these vectors are just collections of 3 floating point values. And I probably should have started here, but there's a types file, and anytime I'm programming, something major in C or C++, I make a types file. And what this types file is for is to include the type definitions and pound defines, the macros that I use that help me to understand the scope of the code that I'm writing and the size of the data that I'm working with. So for instance, and also this is sort of a modern convention. There's a lot of low-level developers who are doing things this way. I know that if you code in Rust, the basic types are done in this way too, just out of the box. But you'll see that I have char, short, int, and long, which are these basic data types, redefined as this S8, S16, S32, S64, and then the unsigned versions defined as, these, U8s to 64s. And so why am I doing that? Well, I do this to understand the impact that the variables that I'm creating, how they are, like what they're doing in memory. and the size that they're taking up. So for instance, I know that a char is 8 bytes, and by default it's signed. So that means if you have a like an 8-bit number, bit 7, so 8 bits, 0, 1, 2, 3, 4, 5, 6, 7, that 7th bit is going to represent if that number is positive or negative. So right there, you already know that there's a max number a max value that variable can have before it flips over to being a negative. Well, the unsigned version is, take that principle, but then the last bit is used for storing, value. It's all positive. So and it's just a shorthand. Not only does it keep my code small and concise, but it also helps me to understand the impact of the variables that I'm working with. So, for instance, I have this struct for our alpha, red, green, and blue pixel data, and so you have 8 RGB values, and each one has a byte. So a byte for the alpha value, a byte for red, green, and blue. And each one of those values goes from 0 to 255. So right there, we know that that's an unsigned byte. So I can just, instead of just using chars or something else, I just say U8. And this is the convention I use throughout all of my code. And so for these variables up here, this one we went over in my video on how I make libraries. And it's just a simple way, at least on Windows, to designate a function as being part of an API. So it's going to be consumed somewhere else. And the word static has a different meaning depending on its context. So when used as a function, it means that it's internal to that translation unit. So for instance, these are all external. Let me find a good example. Yeah, reclaimer core. Yeah, right here. So the Straussian grid. This is something that's called from within this library. So there's another function in here that calls this, and there's no need that this would ever need a specific instance for something else. So I just designate that as an internal function. And for local persist, this is a way of saying that a variable is going to have the same value when that function completes and then comes back. So for instance, I think I use local persist in my Win32 platform. Let's see. Yeah, so for the I/O for the mGUI library, I don't really need to be creating and deleting this variable like every single time. And here's more, like this window rectangle. I keep that there just because it's something that I can always keep in memory. It'll always be there, and there's it's called every single frame. There's no reason why I would need to reinstantiate that every single time. And it's also handy for when you're calculating delta time, because if you have the current time stored in local persist, that you can just move to previous time or vice versa, but you get the idea. You have something that you can store every time, and it'll be there when you call that function again. So if there's variables you're using every single frame, using a static, or as I like to call it, local persist, or just local, I'm probably just going to rename that to local. And then there's what we actually mean by global variable, and that's global. And I think I lost that again. Yeah. And so global is what we actually we're now, I think everybody understands what a global variable is. If that file is included anywhere, you can access whatever that variable is. I used to store global variables for the APIs, but now I'm actually containing those. So that's a little overview of the code base, how it currently looks, and how I currently do things. And like I mentioned before, this is not meant to serve as a definitive guide for how things need to be done. It's just how I'm choosing to do things. So I just have this blank canvas here that I wanted to show, and there's going to be things that I'm working on, and updates to the game are going to be coming out as they are in a presentable state. And so the next thing I'm going to work on is there's inconsistencies between how things are rendered depending on the hardware that I'm using. So for instance, this doesn't look like this on my laptop. It If anybody knows what to check, feel free to message me. But I use the Learn OpenGL uh, for reference. It's a fantastic website. It also exists as a book, but it's completely, excuse me, it's completely free online, and it includes all of the source code. So you can just run the source code for each exercise, and it works on all the computers that I have, but in this state, it only looks like this. Like my code only looks like this on my desktop. On my laptop, it's just the skybox and nothing else. If I'm only rendering the this cube and the grid, it looks fine. But as soon as I draw the skybox, it wipes everything out. So I have no idea what's going on. I need to fix that, and I'm eventually going to start probably improving these camera controls, having a more formal debug interface where I can actually interact with things on screen, and start working on the main character for the game. And when I'm introducing the character, I'll start introducing a little bit more of the character's backstory and why he looks the way that he does. He's probably going to be a very simple placeholder, like something very blocky that I threw together in Blender that looks similar to a Minecraft character, but it'll work in terms of having a placeholder that I can use to position an over-the-shoulder camera. And, if we could do that, I would say we'd be in pretty good shape. And so um, I'm going to keep everyone updated as, like I said, when features and fixes for this game are in a presentable state. I said this was going to be a quick video, but it turned into like a 30-minute one. But I just appreciate everyone who's here, who stuck with me, and I will see you in the next video.